Hello everyone, welcome back to Next Gen Chemophiles. In our previous video, we learned about Valence Bond Theory, which explains bonding through the overlap of atomic orbitals. But VBT has some limitations, especially when we try to explain the paramagnetic nature of oxygen. So, how can we understand this better? The answer is molecular orbital theory, or MOT. What is molecular orbital theory? Molecular orbital theory was developed mainly by Friedrich Hund and Robert Mulliken. According to MOT, when two atoms combine, their atomic orbitals do not simply remain separate. Instead, they combine to form new orbitals called molecular orbitals. Simple analogy: imagine two musicians playing together. When they combine their sounds, they can produce a stronger, more stable sound or a weaker, less stable sound. Similarly, when atomic orbitals combine, they form bonding molecular orbitals and antibonding molecular orbitals. When two atomic orbitals combine, the total number of molecular orbitals formed is equal to the number of atomic orbitals that combine. For example, two atomic orbitals result in formation of two molecular orbitals. These are 1. Bonding molecular orbital. It is formed by constructive interference. The electron density increases between the nuclei. This lowers the energy and makes the molecule more stable. 2. Antibonding molecular orbital. It is formed by destructive interference. A node is formed between the nuclei. The energy increases and the molecule becomes less stable. It is represented by an asterisk, sigma star or pi star. Molecular orbitals are mainly of two types: sigma molecular orbitals, formed by head-on overlap. They have electron density along the internuclear axis. Pi molecular orbitals, formed by sidewise overlap. They have electron density above and below the internuclear axis. Rules for filling electrons. Electrons occupy molecular orbitals according to three important rules. 1. Off-Bohr principle. Electrons fill the orbitals in order of increasing energy. 2. Pauli exclusion principle. An orbital can contain a maximum of 2 electrons, and they must have opposite spins. 3. Hund's rule. Orbitals of equal energy are singly occupied before pairing occurs. MOT also helps us calculate bond order. The formula is bond order equals number of electrons in bonding orbitals minus number of electrons in antibonding orbitals divided by 2. What does bond order tell us? Higher bond order means stronger bond, shorter bond length, greater stability. If the bond order is 0, the molecule generally does not exist as a stable molecule. One of the greatest advantages of MOT is that it explains the magnetic behavior of molecules. If a molecule contains unpaired electrons, it is paramagnetic. It is attracted by a magnetic field. If all electrons are paired, it is diamagnetic. It is weakly repelled by a magnetic field. Example: oxygen molecule. According to MOT, the oxygen molecule contains 2 unpaired electrons in its antibonding pi molecular orbitals. Therefore, O2 is paramagnetic. This is something that traditional valence bond theory cannot properly explain. This is one of the major successes of molecular orbital theory. Advantages of MOT: explains the stability of molecules, calculates bond order, explains bond strength and bond length, explains paramagnetism and diamagnetism, explains electron delocalization. Limitations of MOT: molecular orbital diagrams can be complicated. It requires more mathematical treatment for complex molecules. It can be difficult to apply to very large molecules. Conclusion. Let's summarize. According to molecular orbital theory, atomic orbitals combine to form molecular orbitals that belong to the entire molecule. Electrons are distributed among bonding and antibonding molecular orbitals. Remember, MOT gives us a more complete picture of chemical bonding and successfully explains properties that other theories cannot. If you found this video helpful, like, share, and subscribe to Next Gen Chemophiles. Thank you for watching.